Perhaps you know that in Newtonian mechanics, the interaction between particles or bodies, let's say the sun and the planet, the interaction speed is infinite. So immediately when this is doing something, the planet will feel it immediately. And in relativity, it's stated that nothing moves faster than the speed of light, not even gravitation. And also in relativistic electrodynamics, point charges can't interact faster than the speed of light. And for fun, here I use an expression taken from relativistic electrodynamics, but adjusted to gravitation instead. So we can see what happens in a system where there are delays. It takes some time for the interaction to spread out to here. So, but we still use Newtonian mechanics, so F equal ma and things like that. But we introduce a delay by using this expression here. So here are those parameters. So the first we can do is to Taylor expand this expression here for relatively small speeds, um. So that's the speed of this guy here. And if that is slow compared to the speed of light, then we can expand this square root. And we can do things here. So what you get is the following three terms. And everything else will be higher order, like, u to the power 4 and c to the power 4. Things like that. So now we have a little bit simpler expression, and here you can actually notice that this is the standard Newtonian field, the G field. So we have a field here from the sun. It's that one. But there are some other terms here trying to take into account that the interaction is delayed. So that's those terms here. And let's, within Newtonian mechanics, let's introduce the delay. So in classical mechanics, it's still like this, ma. So the acceleration will be just g here. And in a similar way as this expression is derived, you can also derive the expression for the sun, capital M, because that will also feel a field from that guy, from the planet. So that's that. And if we are smart and use a center of mass reference system, i.e. a coordinate system, then the speed of the sun is like this and the planet like this. So there is a relation. So we can replace the here using that. And then those terms here look a little bit more similar, don't they? If it's both the planetary speed here and here. So we can use that. And what we get when we take the relative acceleration. So this is the acceleration of the planet relative to the sun. And then you get this expression here. And obviously I cannot show all the details because the video would be too long. But this is just the Newtonian part. And in Newtonian mechanics, for a two-particle problem, there is no precession of the orbit. So we immediately know that that's not going to contribute to anything. And if you look at the detailed integrals used to derive orbital precession, one can find that the integral must be 0 or this kind of term. So let's not worry about that. Just say no precession for that. And here is the sole contribution that actually gives orbital precession, is this term here. And usually we are not using expression like this. We are usually using the relative orbit, so it's just one particle problem in that case. And since this is the case, one can derive the relation between this speed here and the relative speed. So it's like that, and then this term that is of interest looks like that. And now we can put in the relative velocity instead. And it's because the integrals for orbital precession are adjusted for the relative orbit. So when we have it on this form, it can easily be put in to those integrals that I can't show you here because it's too complex. But this is the result we get. And here is a precession formula for those kind of terms. And gamma here, it's related to this term here, 2g and the reduced mass, mu, and it's a negative sign here because of how it's defined in the derivation. And the second sigma here, for our case here, there is no such term, so we can say sigma equals 0. So this is the thing to calculate the orbital precession, the advance of the perihelion of the elliptic relative orbit. So let's look at this. Yeah, okay, that's like this. Exactly like this. And suppose the mass is very small compared to the sun, then this term disappears. And so the end result in our solar system is like this. So, and if the mass is very small, like a test particle, yeah, then gamma will go to 0 completely. And as sigma is 0 here, the precession will be 0. So there is no precession at all. So let's compare that to general relativity. The same result would be this instead. And you let m go to 0, you're still left with 3g capital M. And so there is a substantial orbital precession in general relativity. For example, for a Mercury, it would be 42.983 arcseconds per 100 years. And obviously, this here is not the good result. First of all, m is very, very small compared to the sun. So this is a very, very, very small term. And it's also negative, so it's the wrong sign. So unfortunately, Newtonian mechanics cannot be saved by introducing interaction delays, because you only get the completely unphysical result, which is not in agreement with experiment. So can we even understand this result, that for small masses there is no precession? Well, look at the speed of the sun is related to the speed of the planet like this. But if this mass is very small, then it will not affect the sun. So the speed of the sun will go to 0 if it's just a test particle. And what will happen to this expression then? This goes to 1, this goes to 1, and this goes to the Newtonian G field, where the speed of interaction is infinite. So there is no delay here and no precession in Newtonian mechanics for the two-body problem. So one could say a small mass, in that case the sun is never moving, so it's a static field that this mass is moving in. And if we calculate that G field at time equals 0 or time equal 1,000 years, it's the same field at all times. So the delay does not matter in this case. So If this was interesting, like and subscribe. Bye bye.